connecting to that. There we go. We're all good.
Right. Okay. Well, it's a pleasure to introduce Simon Murphy. Simon got his PhD back in 2013 at UCL in the UK with Don Kurtz, working on the pulsations of A-type stars and seeing what we could understand more about those pulsation Kepler data. And then, well, Simon continued his career in Australia, first in Sydney for a few years, and now he's a ARC Future Fellow and Associate Professor at the University of Southern Queensland. And since his PhD, Simon's been tackling this very thorny case of pulsations in A-type stars, but with quite some spectacular results over the years, and in particular in using the phase modulation of the pulsations in these clocks, if you like, to detect companions to A-type stars, planets, or secondary stars. And also now, I guess lately, he's been focusing on trying to use the spectra, or at least the simpler spectra among those stars, to infer precise and accurate ages. And I believe that's the topic of the talk today. So thanks again, Simon, for being available to deliver this, and the floor is yours.
Thank you. Thanks for having me. And yeah, this isn't work that I've done in isolation. This is the efforts of many people. I've got my collaborators on the slide here, Tim Bedding in particular, who I indeed worked with for around 10 years. I intended to go to Sydney for 2 years to work with Tim, and I stayed for 10. Anuj Gotham, who was a PhD student at UniSQ, and perhaps you recognize many of the other astroseismologists' names there. So I thought I might start off by explaining how difficult stellar ages can be to determine. So this here is an age map of the Scuti star forming region. So this is just latitude and longitude on the sky, and in color here is encoded the stellar age. And so you can see there's a strong age gradient across the sky for this association, ranging from around 5 megayears in the blue in the top left to 30 or so in the lower right. But superimposed on that age gradient, there is also a lot of age dispersion. So there are older regions, such as this one, that are embedded around areas that are younger. And so this can make it quite difficult to determine ages for individual stars. So if you were interested in one particular star in the association, you could attempt to use an age map like this to read off an age, and you might get something like 14 megayears, plus or minus 1 for how well you can read the color bar, and then plus or minus 3 megayears for all the systematic uncertainty that goes into making a map like this in the first place. But with asteroseismology, we can actually model that age. And for this particular star, we get an age of 10.7 megayears with an uncertainty of around 10%. So we can actually do quite a lot better. And in this case, that indicates that this star is on the 3-month sequence. So that's sort of the overview of what we're about here, is trying to do asteroseismic ages and see how they can complement what we can get through other means. So how do we usually determine stellar ages? Well, we usually map a bunch of observables. So those could be parallaxes. You might have space velocities, spectroscopic temperature maybe. If you're really lucky, you might have some interferometric information, maybe some multicolor photometry. We map those observables into some stellar parameters. Those would be mass and metallicity, the age that we're interested in, and maybe some other physical effects like rotation. The most commonly used method to do this would be stellar isochrones, which are great most of the time, but not always. If you have isochrones of different metallicity, those can overlap and make it difficult to work out what's the true age of the star. Pre-main sequence isochrones will overlap with main sequence isochrones, and the results are very dependent on those observables that we were just talking about. So if you want to measure the main sequence turnoff or something, then isochrones are fine. But if you're talking about individual stars, you can have some large uncertainties. So we can turn this into a problem statement. Imagine that you have a star that has a planet-forming disk. Now, disk evolution is very rapid. It happens on timescales of a few megayears, and so precise ages are really important. But what if your star is obscured by a disk, or it's in a dusty environment? Well, then you might get the wrong luminosity. Or if the metallicity that you've measured for the star has been influenced by the fact that that star has a disk and there are planets embedded in that disk that are accreting material, You get selective accretion onto the star, and you might end up with the wrong metallicity. Early type stars might rotate rapidly. In fact, the mean of the rotation velocity distribution is around 150 kilometers per second for mid-A stars, and some stars rotate more rapidly than that even, and that causes stars to become oblate, and so they have different temperatures and luminosities compared to non-rotating stars of the same mass. And that rotation can also give you extra mixing, which changes your main sequence turnoff. So as you can see, there are many effects here that can be problematic. Now, there are also other age indicators, empirical age indicators. You might have gyrochronology, use the stellar spin down as an indication of the stellar age, the lithium depletion boundary, and others. But those are really only applicable for cooler stars, like sun-like stars, and they are only really applicable in certain age ranges. They don't really help you if you're trying to ascertain the age of a single star with a planet-forming disk. So for a familiar example, we can turn to the Pleiades. The Pleiades is a young nearby open cluster. You would expect us to do pretty well at inferring an age. But we actually find a wide range of ages in the literature from isochrones, and that can depend on how you treat rotation. So you get a 60 mega-year difference whether or not you include rotation. It's a huge difference. And that's because of two main effects. I mentioned this one before, the star becomes oblate. So gravity darkening causes the temperature you measure at the equator to differ from the temperature you would measure at the poles. The same is true for the luminosity. This all depends on the observing angle. The degree of that deformation scales as the square of the stellar rotation rate, so your really rapid rotators are really strongly affected. And you get these brighter poles, the cooler, darker equatorial regions, and that displaces your star with respect to isochrones. So that's the first main effect. The second effect is you get extra mixing of material. So large scale flows inside the star will cause more hydrogen to be mixed into the core. That will extend the main sequence lifetime, which is a big problem if your goal is to measure the main sequence turnoff using isochrones. Right? There are other systematic uncertainties that give rise to the wide variety of ages we see in the literature. For instance, lithium depletion ages will depend quite strongly on the sample selection and on the model physics. So whether you use, say, brown dwarfs or not, or whether you include magnetism can have quite a big effect on your derived age. There are large systematic uncertainties associated with the depletion method. That's because of the effect of star spots and of differential rotation, which give you systematic uncertainties. Oh, okay. They'll give you systematic uncertainties of around 10 to 20%. In fact, that age map that I showed you on the first slide, that was constructed using lithium ages, and that had a 25% systematic uncertainty embedded within it. And don't forget that any age uncertainty that exists for young clusters like the Pleiades necessarily extends to all the other clusters that we analyze, because all of the ages that we construct for these clusters, they're all relative. Right? The better you can do at the young associations and the young clusters, the better those ages will propagate to older things that we study. So for the Pleiades itself, most of the ages that we see quoted are around 100 to 160 megayears. There's only been one asteroseismic study, one study using stellar pulsations to measure the age of the Pleiades. That was back in 2006, and unfortunately, they used a hard age prior of 70 to 100 megayears, which is outside of the currently accepted age range. So we don't really have a modern study of the Pleiades with asteroseismology. But my message for everybody today is that asteroseismology can provide those precise stellar ages that we want. There's only a weak dependence on the typical observables, so we use temperatures as a prior rather than as a hard cut on the sample selection. Dust obscuration, not a problem for asteroseismology. You still measure the same pulsation frequencies even if there's dust in the way. It might affect your luminosity, but again, that's only used as a prior. It's not used as a hard cut, or it shouldn't be. This can work for single stars. You don't need a large population, although there are cool things you can do if you have large populations. You can measure the rotation asteroseismically, and so you can properly account for it in models. And look, model physics is always going to be a problem, but at least we can work on that model physics. So if we include eclipsing binaries, for instance, we can help parameterize things like core overshoot, which are a large uncertainty in some models. So the bottom line is that we can improve cluster age benchmarks and therefore improve the whole age scale that we're using. So that's sort of the goal of my, my future fellowship. So to come back to that case study, HD 139614, we can ask why we need these precise ages in the first place. This star has a warped disk, it has ring structures, and it has cavities. So I'll highlight some of those here. So this is a polarized scattered light image, and there's a ring around the star in polarized scattered light. There's a couple of arcs that you can see around the edges here, and they're labeled in this panel here. And those are indicative of a planet that is orbiting within this disk. On the right-hand side here, this is a model, but you can see there's an inner disk, and then there's a gap that's been carved out, presumably by a planet, and then an outer disk. And so we're going to see that even in cases like this, asteroseismology can offer you precise ages. So how does asteroseismology work? I'm sure you've all heard many talks about asteroseismology in this department. The idea here is that different pulsation modes penetrate to different depths throughout the star, which means that all of those modes will sample the internal density profile of the star in a different way. So if you can measure the mode frequencies and you can work out which mode they are associated with, you can probe the interior structure of the star. That's the fundamental idea of asteroseismology. But in order to do it, you need to be able to identify the modes. You need to be able to assign these quantum numbers, the radial order n, the degree L, in order to get out that internal density profile. Now, in asteroseismology of sun-like stars, sometimes we forget about labeling individual modes, and we use what are called scaling relations or astroseismic indices. So you have nu max, which is the frequency of maximum power. So that's this sort of Gaussian-like envelope, which sort of encloses all of the modes of the star. And then we have this other quantity, delta nu, that again, I'm sure you're all familiar with, which is just the frequency difference between consecutive modes of the same degree, that are one radial order apart, right? But the best results come when you can identify individual modes. So when you can apply these degree labels to each mode, you can say this is L equals 1 mode, this is L equals 0 mode, and so on. But I'm not working on solar-like oscillators, I'm working on delta Scuti stars. These are about 1.5 to 2 times the mass of the sun. I've got an evolutionary track here of a 2.1 solar mass star. And so these delta Scuti stars are located at the base of the classical instability strip where it intersects with the main sequence. These stars eventually become red giants on timescales of about a big year, and so many of the red giants that you're all studying here could once have been delta Scuti stars in the past. And historically, we've kind of failed with delta Scuti stars. It seems that stars that lie near each other on the HR diagram have some seemingly random subset of modes identified. There's been no delta nu to speak of, so we haven't identified regular patterns of pulsation modes. And without those regular patterns, the mode IDs become intractable, meaning we can't label each mode with its degree. And then without those labels, you can't do asteroseismology. But a few years ago, we had a breakthrough. This was a paper that was led by Tim Bedding that was published in Nature, where we found very regular high-frequency pulsation patterns in these young intermediate mass delta Scuti stars. And so here on the right-hand side are a bunch of Fourier transforms of test light curves, where we see regular cone-like patterns of pulsation modes. Now, we still don't have those really nice Gaussian envelopes that we have for solar-like oscillators, but what we do have are regular spacings that allow us to identify pulsation modes. So it basically reintroduced the asteroseismic large spacing, delta nu, as a new observable for delta Scuti stars. So if we go back to our case study, HD 139614, here are its test data which show that it's a delta Scuti star. The light curve is on the top, the Fourier transform is on the bottom. So each peak in this Fourier transform is a pulsation mode, and I've labeled that with a degree, either a radial mode of L equals 0 or a dipole. And what I've also drawn on this are intervals of 6.83 cycles per day, which is the large spacing for this star. And so if you look at any particular window between 2 dashed lines, you'll notice that the dipole modes are always on the left-hand side of each window, and they are regularly spaced. So this star has these regular frequency spacings, and this value of delta nu, 6.83, is actually quite large. So delta nu scales as the square root of the mean stellar density. And so if you've got a large delta nu, you know the star is very dense. And so in this case, we know the star is very young, which is a surprise. I would have told you it has a planet-forming disk, so it's probably pretty close to the zero age main sequence. Now, when we analyze these stars, we use a tool called the shell diagram. Again, many of you may be familiar, but I'll just walk through what we do here. We take our Fourier transform, we divide it up into equal segments of size delta mu, and then we stack them vertically with the highest frequencies at the top. We encode amplitude information with color, and that forms the shell diagram. That was a bit quick, so I'll just run through that one again. We take our Fourier transform, we divide it into equal sections of size delta mu, stack them with the highest frequencies on top, and encode the amplitude information with color. So darker color is stronger peaks. Those are where the modes are, and that makes our shell diagram. So here's what the shell diagram looks like for HD 139614. We have a bunch of strong peaks. I'll try and remember to use the mouse. We have a bunch of strong peaks here. We also have many weaker peaks. You may remember that the dipole modes were on the left-hand side of each window, and so they're also on the left-hand side of the shell diagram. The right-hand side of the shell diagram is just a repeat of the left-hand side. So this is a bit like when you make a phase-folded radial velocity curve, and you just add the last 20% back on, so that you find it easier to track effects that happen across the edge of the diagram. So what we notice is that the dipole modes all fall down the left-hand side of the diagram, which makes them really easy to identify. The radial modes have this sort of curved ridge at the center of the diagram, and this basically wasn't possible before. We had no means to infer the mode identities before, but now we can identify several modes in the same star. That really allows us to do some asteroseismology. So what we do is we compare these observed modes to stellar models. You have to be really careful when you do this that you get the mode ID correct. It's not the case that the strongest peaks necessarily are the ones that you want to be modeling. So on this particular row here, there's a strong peak here, which is probably a rotationally split mode. But if we're only modeling the zonal modes, those with m equals 0, which is all you can model if you have non-rotating models, you might find it's not the strongest peak that you're after. And so the way we accounted for this was we constructed 10 different mode ID scenarios where any mode that we were not certain of, we've created an alternative scenario for it. So that would include this particular dipole mode I just mentioned, this radial mode over here, which could plausibly be either one of the pair, and also the fundamental radial modes, that's the radial mode with n equals 1, which did not appear to match with any peak in any of the scenarios. And what we do is a bit of grid exploration. So we calculate a whole bunch of stellar models. The models themselves are calculated in MESA, the pulsation calculations are done in Gaia. And we start off with the classical error box. So that's the temperature and luminosity, but they're not hard priors, and we expand the grid as we chase the lowest chi-squared in the solution. We start off with roughly solar metallicity, but again, we expand it on either side. And we also start off searching only ages younger than 30 megayears, because we know this star has a planet-forming disk. There's no need to calculate gigayear models, right? So this is a grid in mass and in metallicity. This is metal mass fraction. The sun is about here in the middle. And each point in this grid is an entire evolutionary track that is sampled at hundreds of different ages. And what we're plotting in color is the lowest chi-squared of any model along the track. And we can see that we have, we've found the global minimum here, and we've expanded in each direction around it in mass and metallicity. And so we essentially proceed like this, and we chase the lowest chi-squared until we're satisfied that we've sampled space. Well, at least that's how we used to do it. Now we have some better tools. This is some work that I did with many of my colleagues at the University of Birmingham to train some neural networks to do this for us. So when you're using MESA and Gaia, it takes about 15 minutes per evolutionary track that you calculate on an HPC. And what you end up having to do is calculate an entire evolutionary track. Then you have to run the pulsation code on each profile or each model that you've calculated. Even after that, you end up limited to the precision of the grid. If you only used 0.05 solar mass spacings in mass, then that's the limit of your precision, right? And then even after that, you can end up with bimodal solutions and the uncertainties that are very difficult to analyze because your grid is so quantized. But with a neural network, you can perform evaluations in just 1 microsecond. And that allows you to do Bayesian sampling, sort of Markov chain Monte Carlo style, where you can take tens of thousands of draws for the same star and work out what the best fitting parameters are. So Owen led this study. He's a PhD student. He trained a neural network on the grid of models that can then be applied to any star. The cool thing is that you get robust parameter estimation out of it, so not just your mass and metallicity and age, but good uncertainties on those too. And I'd also like to mention Anuj Gotham here. He's a student of mine at USU. He is working on the next generation of this model grid where we include rotation. So he's taking this grid from 200,000 models to 20 million models, and is including rotation, but is also estimating systematic uncertainties like the effect of different core overshooting or mixing lengths or things like that in models. So when you do this for HD 139614, here's what some of those parameter interdependencies look like. There are some correlations between, say, metallicity and age, but we're talking about rather small ranges in age. This is age in mega years, and so ultimately we end up with 1% precision on mass, 10% precision on the metallicity, and 3% precision on the age. We happened to find that there was no dependence on the mixing length in this star, probably because it's very young and it's recently been homogeneous because the whole star was recently convected. For older stars, there might be mixing length dependencies. But this is just the precision. This is just the relative precision that you get between models. You have to remember that there is no systematic uncertainty added in here to describe the accuracy of the modeling process overall. And so a better accuracy estimate for the age would be about 10%. And again, Anuj's PhD thesis is actually trying to quantify that systematic uncertainty. Another cool thing that we get out of the neural network is posterior predicted oscillation frequencies. So those are shown on this Eshel diagram with squares. And where you get a really square shape, that means that the posteriors are really tight. They're saying that is where this frequency should be in all 100 frequencies that are plotted. But where they're spread out into a bar, that's saying, oh yeah, the mode could be here somewhere, but it's not so well constrained, right? So that's actually a pretty useful thing for a couple of reasons. One is that, of course, the modes that you used as constraints in the models should overlap with the posterior predictions, right? So like this one here, this mode falls pretty nicely into this tight square. It says, yeah, we think we've got that mode labeled correctly. But also if there were additional modes that, if you had a really strong peak here that you hadn't labeled, you'd be pretty confident if those posterior predictions fell on top of it, that's an extra mode you could identify. So that's just a little useful tool that we have in the arsenal by means of using a neural network. And this works for many young stars and associations. This isn't just an isolated case that applies for one star. Here are 3 other stars. These were first found in Tim Benning's Nature paper. I remodeled them last year. And so we can get masses, ages, metallicities for lots of different stars. We can start doing this sort of wholesale rather than doing it on a star-by-star basis. The time-consuming element of this is getting the mode IDs right in the first place. And this gets more complicated when we include rotation, because in some stars, such as this one, there's sort of a parallel ridge here, which would be your rotationally split mode. So these are probably the prograde dipole modes. We can try and model those too. It just takes more time and effort. So that leads me nicely onto the second part of this talk, which is population statistics and clusters. A lot of this work was based on an undergraduate project that was done by William Young at USU that I supervised for 2 semesters. And this is sort of the money plot of his work. This is an HR diagram with hundreds of delta Scuti stars whose delta mu's have been measured. There's a lot of information there, but first let me talk you through how we get there. If we want to do population statistics, we need a large sample. For a large sample, we need to somehow automate the ridge detection with shell diagrams, or in other words, automate a method for measuring delta mu for all of these stars. Now, in the Nature paper, we just used autocorrelation. The autocorrelation of the Fourier transform tells you what that spacing is, and that's fine. It's proven, it's simple, it's robust, but can we do better? So what Will did, what Will did was trained a machine based on a bunch of features, and those features included how vertical the ridges are in the shell diagram for a given value of delta nu, what is the scatter of the points along that ridge, what is the length of the ridge in the shell diagram, whether there are gaps in it, and indeed he included the autocorrelation. And that quite neatly separates sort of the bad stars, where there are no patterns in the frequencies, from the good stars where we have nice patterns. Once you've trained your machine, you need to apply it to a large sample. So he first started off with almost 300,000 test stars that had 2-minute cadence data. He made a cut on temperature, which includes the delta Scuti and stability strip plus a couple of thousand Kelvin either side. And that gives you 45,000 ANF stars to start off with. One thing you might notice is there's an overabundance at the zero age main sequence here. So there's a lot more points just here in this diagram than there are higher up. That is a known, what would you call that? That's a known selection effect. It's a bias that we have because we notice that the young stars have nicer patterns. And so when there was a call for which stars do you want to analyze at 2-minute cadence, we said all of the young ones. So that is a known artifact of our selection effect, but it doesn't actually cause us any problems. So we start off with 45,000 ANF stars, and then we have to work out which ones pulsate. And there's a nice trick for this. When you calculate the Fourier transform of a test light curve, you end up with an array of frequencies and an array of amplitudes. You can calculate the skewness of that array of amplitudes, and that will tell you whether the star is pulsating. So if you've got white noise, you'll have zero skewness. If you've got various noise, like you might have instrumental effects or something like that, maybe you've got a granulation signature if you're working on cooler stars, then you'll end up with low skewness in your array. If you have strong pulsations, where you've got sharp peaks every now and then, you'll end up with a really strongly skewed amplitude array. And you can use that to distinguish pulsators from non-pulsators. And that was something that I worked on in 2019. It was also part of a different undergraduate project that Nick Barber led, which was a sort of a feature-based classification of Kepler and test light curves. So even just with a skewness, you do a pretty good job here. You can also add the signal to noise ratio of the strongest peak if you want to add different features in there, but it's not actually necessary. And just applying a simple skewness cut does a pretty good job of separating pulsators from non-pulsators. So it gets about 9,241 pulsators. And then you basically apply your machine that you've trained. So that consists of the 5 features. He also manually confirmed every star that it spat out, and comes up with 340 delta Scuti stars that have regular frequency spacings identified. So that's 6 times the size of the sample that we had from some embeddings nature paper. So that allows you to do some population statistics. We find that there are more stars with nice patterns than the ZAMs. Now that does suggest it's just the younger stars that have the regular patterns. But we also have to acknowledge that we have a selection bias. We specifically targeted those younger stars, right? We also see a gradient in delta nu in the HR diagram. So the delta nu is encoded with color here. So higher delta nu means denser stars. As we expect, the stars that are towards the lower left, which are smaller and denser, have higher delta nu. And as we move up and right, those values of delta nu tend to get lower. That is also expected. As stars evolve, they move up, they move right. And so we expect to observe those smaller values of delta nu higher up. The red stars there are the stars that were included in the nature paper in the first place, which have a relatively broad distribution across the granular space. And so that was actually kind of almost by accident, just a nice representative sample that we had. Now you can make a histogram of all these values of delta nu, and this contains a lot of information. So Will's work showed that you find delta nu values from about 5 cycles per day to 8 cycles per day, so quite a wide range. For reference, all stars in the Pleiades that have measurable delta nu have values between about 6.7 and 7, so they would be quite close to the strong peak in the histogram. Now, the fraction of stars that have discernible patterns actually goes down as stars evolve, right? So as your stars evolve, you start to get mixed modes, you get mode bumping in these stars, and so the patterns get spoiled, which explains why there's a decrease in the number of nice patterns when you go to older stars which have lower delta. You need very high densities to get delta nu near 8 cycles per day. So that requires a really low metallicity, because lower metallicity stars are denser. That's basically because there's lower opacity, and so the star, the effect of opacity is to increase, right? So a lower metallicity, less opacity, denser star. And you need a truly ZAMS-A. You need the star to be at its densest point to achieve delta mu near 8 cycles per day. Even then, if your star is rotating rapidly, that will make it oblate, it will have a lower density, and it will be found at lower values of delta mu compared to non-rotating models of the same. So it's very hard to get very high values of delta nu, and so there are fewer stars found there. It's very easy, however, to get a delta nu of around 7. That's achievable with a wide range of metallicities and masses. We've shown that with stellar models. That sample of stars, or stars with delta nu near 7, could also include stars that would have been up here were they not rotating, but the rapid rotation of the oblate shape has pushed them to lower values of delta nu. It also allows for some evolution before or after the ZAMS. Your star doesn't have to be at its densest point to have a delta nu 7. It could still be on the pre-main sequence. It could be 200 million years old, and you could still achieve a delta nu of around 7. But we must also acknowledge there is a chance for methodological bias here. As always happens when you're training a machine to do your analysis for you, you get out what you cover. If your training is not good, you'll just find the same thing. And this was indeed based on undergraduate work. Will was mostly left unsupervised to develop his tools here. We met once a week. He did some really great analysis. And I'm not saying anything disparaging about him, but there's only so much time you can dedicate an undergraduate project to iron out all of these kinks. But I think he did a really good job, and I think this histogram is really interesting. Now, about the stars in the Pleiades that I mentioned before, I think the Pleiades is another, I think it's a great cluster for us to analyze again because it's nearby, and there are a couple dozen delta Scuti stars that we can analyze. So there are, I think, 30 high-frequency delta Scuti stars in the Pleiades, and they form a nice main sequence in a color magnitude diagram. Some stars don't quite fall on the sequence, so this delta Scuti star here might be reddened. So it might actually belong over here somewhere, but it got reddened and pushed to the right of the diagram. There are also delta Scuti stars up here, which could be binaries, and that's why they sit above the sequence, or it could be due to rapid rotation, because rotation, as I said, makes a star oblate, changes the observed temperature and velocity. It pushes stars to the upwards and or right in the color magnitude diagram. But we see a nice main sequence here. I think there's heaps more work to do with the Pleiades, and Anna's just going to look at this when he's finished his paper on his grid of models. He's going to try and determine an asteroseismic age for the Pleiades stars. For the rest of the talk, I'm going to look at a different association, a younger association with many more stars. So this is the SEP-HER association, Cepheus Hercules, and this is really more of a complex of a few different associations of different ages that range from about 20 megayears up to 100 megayears. So there are several hundred stars in this association. If you take a cut on color, this is a really broad cut on color that includes B stars and goes down to F stars. You can see quite neatly a group of delta Scuti stars that look like they are the main sequence pulsators of this cluster. And so in this bottom panel, I'm plotting only the delta Scuti stars. And I'm using the Gaia-Rui parameter in color here. So this is the renormalized unit weight error. This is a parameter that basically correlates with binarity. So if your astrometric fit has some anomalies to it and it doesn't seem to correspond to a single star, then you'll have a high Rui value. That is indicative of binarity. And that actually works pretty well in this diagram, right? So if we have this sort of zero-age main sequence group of stars, then we see that some fraction of a magnitude above it, you have a bunch of yellow stars, which are presumably binaries. There are also many stars that are probably not association members. So these are on the cluster membership list. They might have low membership probabilities, but we can see just from making this color magnitude diagram that these stars don't seem to belong in the association, or they just have really large parallax errors, right? Which mean that they appear brighter than they should be. So if we if we take this to be the zero-age main sequence population, so these delta Scuti stars down here, we can define a line which would be the sort of minimum luminosity of these stars, which I'm going to call the ZAMS line, right? So this roughly describes where the zero-age main sequence for this association is, and then other effects like rotation and observational uncertainty might jostle those stars up and down a little bit. So we can define a group of stars that's the zero-age main sequence group for this association. In color here, I'm showing nu max, the frequency of maximum power, and we see that there appears to be a correlation in that at the bluer colors, the stars have higher oscillation frequencies. I'm going to come back to that as a main talking point shortly. Now, for some of these stars, it was possible to measure delta nu, not all of them, but some of them. And it was also possible to gather data from Gaia on the rotation rate, V broad, right? It's basically like V sin I, projective rotation rate. So for the stars that we can measure V broad, we notice that the more rapid rotators lie farther from the zero-age main sequence. That's exactly what we expect. That's just an observational confirmation that more rapid rotators are indeed moved up and right in this diagram. So for all the pulsators, we measured delta nu from the shell diagram if we could, and we hope to use that, we hope to use asteroseismology to triage association membership. So on the y-axis here, we have the delta nu. On the x-axis, we have the distance above that ZAMS line, and in color here, we have rotation rate. So delta nu depends on density, right? So as stars rotate more quickly, their delta nu goes down, and they move up in the diagram, so they are further from the ZAMS line. So you expect that the more rapid rotators will be found in the lower right, and indeed they are. But there are some exceptions. There are stars of presumably low inclination. These stars have really low delta nu, but they aren't especially rapid rotators. I mean, they still have V sin I of like 140 kilometers per second, but as far as A stars go, that's not especially rapid. It's not 200 plus, right? And then there are these stars over here that are quite far above the zero-age main sequence line, but they don't appear to be rapid rotators. So those could be binaries. So in other words, asteroseismically, we can determine when stars are simply seen at low inclination, and potentially when the Gaia-Rui parameter has failed to identify binaries. This is actually relatively common in stars that have a lot of circumstellar material, as we might indeed expect stars to. So I mentioned that there was a correlation between the frequency of maximum power and temperature. Now, there's a lot of debate in the literature about whether this relation actually exists for delta Scuti stars. It's a very commonly used relation in solar-like oscillators, of course. But is there a nu max relation for delta Scuti? What I'm plotting here are 5 stars that are in the association. They're plotted in color order, so the number in the top right in each box is the BP minus RP color from Gaia. So these are in increasing color order, and so you might expect their pulsation frequencies to be decreasing as you go down the diagram, but there does not appear to be a simple correlation here. Maybe we can do a bit better and we can actually quantify that. So what we need to do is measure the frequency of maximum power, but how do you do that when your modes are not in a Gaussian envelope? Well, we applied 4 different methods to measure nu max. The reason we want to do this is to identify any methodological uncertainty in this process, rather than just say, take the strongest peak, right? So we use 4 methods. We use the moment method. This is basically like a weighted average pulsation frequency. So you take the product of the frequency and its amplitude, you sum all those up and you divide by the sum of the amplitudes. It's just the moment of the Fourier transform. We do that in amplitude because we use amplitude in our observations, but we also do it in power. Power is the more physically motivated parameter, so we try that too. And then another method that we choose is to heavily smooth the power spectrum. This is something that's often done in solar-like oscillators, is to heavily smooth the power spectrum and measure the center of the power excess. So what we do is we convolve the Fourier transform with a Gaussian of width 4 delta nu. That's the number that Tim Bedding says that everyone who studies red giants uses, so I hope he's right. And we do that again in amplitude and power. And so we end up with 4 methods to measure nu max, and that's why we have 4 dashed lines in each of these panels. Now, sometimes all four methods agree really tightly on the value of delta nu, and sometimes there's a bit more spread. And so if we plot the value of nu max against the color, here the bars represent the maximum and minimum values of nu max that we get for each star from those four methods, right? So that's basically like an error bar. And we see there's a little bit of structure in this diagram. So there are no stars in the upper right above that red line, basically, well, one or two, but that part of the diagram is basically empty. But the rest of the diagram, I don't know, like there's a lot of scatter in there. If you try and fit this with a straight line, with these squares, you end up with a huge amount of scatter that doesn't appear to be particularly useful, right? In fact, if you were to say, where does the relation exist? You might draw a diagonal line across the diagram like this, but then you'd be hard pressed to explain why there are so many outliers. In fact, there are so many outliers, it's hard to say which stars are outliers and which ones aren't, right? So can we do a little bit better with our outlier treatment? So what I'm doing here is I'm fitting a straight line, but I'm also fitting a Gaussian background. And the free parameters in this fit are the mean and the standard deviation of the Gaussian background, the gradient and the intercept of the line. And then there is also a jitter term for scatter about the line. And I'm fitting an outlier probability. So for every single star, it's saying what is the probability that this star belongs in the relation versus exists as a outlier that we can't explain. And look, you can get a half decent relation out of this. It's not particularly physically motivated, but statistically, you can sort of get something that works. But it only works in color. And if you try and translate this into temperature, it just doesn't work, right? The stars are, they're just not in a straight line. They're not in a neat line. And so you can try and cheat a little bit and you can say, all right, what if I use my outlier probabilities that I've made in color space, and I transport those over to temperature and I fit that instead. So that's what the dashed red line is. But even with that generous outlier treatment, you end up with a 370 Kelvin scatter about this line, right? Without that generous outlier treatment, you end up with a 700 Kelvin scatter or more. But the instability strip's only 2000 Kelvin wide. So if 1 sigma, you're covering 1400 of that 2000 Kelvin scatter, like what are you doing? Right? That's not a useful relation, in my opinion. That's basically what I've settled on from this analysis is there is no useful relation between nu max and temperature for delta Scuti stars. And if you can't find it for a large homogeneous sample of stars of the same metallicity and the same age, then what hope have you got for field stars? That's where I'm at. I also tried adding other clusters to see if they behave in the same way, and surprisingly, they kind of do. So there's 5 different clusters here. One of them's Sepher, one of them's Pleiades. You've got Persepi, which is 500 to 700 million years old, depending on which paper you read. You've got Trumpler 10, which is at around 50 mega years. NGC2516 is about 100 mega years old. So they're mostly young except for Persepi. And oddly, they show the same kind of structure, right? Like you have a paucity of stars in the middle that I can't explain. There's a sequence that's basically flat as a function of temperature, and there's a sequence that seems to strongly depend on temperature, but there's no reliable indicator of which ridge in this diagram any given star is going to lie on. And if you are just looking at some random field delta Scuti star and you say, oh, great, it's got a nu max of 40, can I infer its temperature? I mean, what temperature can I infer from that? Right? I just don't see it. That's my summary of whether a nu max relation exists. And then one last bit of analysis that I did for this association is the effect of rotation on pulsation. So if you focus first only on the histograms, in gray we have a histogram of all of the stars in Sepher. In blue, all of those that are delta Scuti stars, and then in orange, those for which we could measure a delta nu, so those that have nice regular patterns. And what we see is that the more rapid rotators are more likely to pulsate, but they're also less likely to pulsate with regular patterns. That sort of confirms another result that just came out a few weeks ago, largely from the Hawaii group, where they found that the pulsator fraction of delta Scuti stars was higher amongst rapid rotators. So that's sort of the first conclusion here. And then what I've also overplotted are these Maxwellian distributions of the, basically the rotation velocity distribution of A stars from the literature. I've done an equatorial distribution as well as a projected distribution. And they would suggest that we have an excess of slow rotators in Sep-Her. So there are many more stars down here than we would expect based on these well-measured Maxwell distributions. And I can't explain that, actually. I have some ideas to do with chemically peculiar stars that you can ask me about later if you're interested, but it's not particularly obvious why that occurs. And then just to wrap up and talk about where the future is in this field, one thing that we can do is directly measure stellar rotation. Right? I talked about this earlier. If you can measure the splitting of pulsation modes, you can model non-radial modes to give you an internal rotation. And then from spectroscopy, or maybe even from Gaia, you might have V sin I or V broad. And then from the stellar models that you're fitting, you get a stellar radius. And then you do some very simple undergraduate arithmetic and you come out with an inclination, right? So that's basically an asteroseismic inclination for your star. Now, if the star has a disk, like our case study familiar, you can measure that disk inclination. You get it from ALMA or VLT sphere, whatever it is that you're using to study the disks. And you can compare that disk inclination to the rotational inclination. And then what you've essentially measured is any spin orbit alignment or misalignment during the planet formation process itself. So you can measure whether planets are born misaligned with their host star's rotation. I think that's really cool. And I'm aiming to do this for 15-ish delta Scuti stars. If you take the number of stars that have disks and the number that pulsate, a rough number we'll get out is about 15. So I've applied for a grant to do this. We'll see. You never know whether you get this money or not, to hire a postdoc to do it. But the reason we want to do this is that if we can measure these disk obliquities for very young planet-forming disks, we can work out whether planets are born misaligned. So planets either have primordial misalignments or they can get dynamically misaligned later on very different timeframes. But what we generally observe is a misaligned planet without knowing how it got there. And if we wait too long, and if the system orbital parameters are right, then you get tidal realignment on timescales of a few hundred million years. And so it's by studying these really young systems that we can work out how these misalignments occur in the first place. And this has really important consequences for the survivability of, say, Earth-like systems if you have a Jupiter-mass planet that's on a misaligned orbit or migrates through this. So this is one of the big questions in exoplanet formation. And I hope that we can study this using the test data and with asteroseismology. A cool little extra here is that with asteroseismology, you can target or you can evaluate whether systems have undergone tidal realignment, because you can measure the internal rotation rate of the star and you can look for signatures of realignment. And I have a rather complicated slide that explains how you can do this. So in the left panel, we've got two different models. We've got a model that has a uniform rotation profile. So the angular rotation rate is a flat function of radius within the star. This is the surface, this is the core. And then there's another one that has differential rotation. So the rotation rate's flat in the core. This just naturally arises from the stellar models. It increases just outside the core for various conservation of angular momentum reasons, and then decreases as you go to the surface. But at the surface, for these two very different rotation profiles, you basically measure the same rotation. So those are the two cases that we're evaluating against. And if you look at the dipole modes and the splitting of those modes into the components, they have very different splittings. It doesn't look huge, but they have different splittings based on the internal rotation profile. So even though the surface rotation rate's about the same, and in fact, the orange one here is slightly higher, the splitting is much larger in the differential case because it's much larger inside the star. And this is just one mode. This is the first dipole triplet. So that's these 3 points here. You can do this for every dipole multiplet that you can measure in the star. These little gray error bars here are the measurement uncertainties that you have on individual measurements here. And so the effect that you're trying to measure is much larger than the uncertainties. And you can reconstruct the interior rotation profile of your star, and that can tell you whether your star has undergone misalignment. So that's everything that I'm working on right now. So in summary, mode identification that was once intractable for delta Scuti stars now isn't. We can now do things, now identify modes. Asteroseismic ages for young stars can be used to recalibrate stellar ages if you can determine cluster ages. Because the cluster ages are often determined relative to each other. If you improve your benchmarks, you improve the whole system. I also talked about HD139614, which is this young planet-forming disk that's still on the pre-main sequence. We get pretty small uncertainties on the asteroseismic age. the magnitude of that uncertainty depends on how many systematic effects you include. But it's also possible to identify modes in dozens of other stars near the centers. I think there's lots to be done with asteroseismology and disco obliquities. If any of you are on the market for a postdoc, keep your eye out next year if I'm successful. And if I'm not, then, well, no job to do with me. And rotation is important, but it's also troublesome and it's also useful. Rotation is just the thorny part of this problem. I've got a lot of different references here that all went into this talk if you're interested. Thank you all very much for your time.
Questions? Okay.
Yeah. I have one. The new max stuff, I was wondering if you could put to the last plot you have.
This one?
Yes, one, yes. Doesn't it almost look like there's two distributions?
Yeah, there's like one that scales with temperature and one that's flat. Yeah.
Have you tried pre-widening out either the 80 to 0 or the 1? Recalculating.
So you mean like if stars only pulsated in radial modes or only pulsated in dipole modes, you get a different answer?
Yeah, maybe. Maybe they have different amplitudes distributions.
That is a good point. Yeah. It could be, for instance, that this one is where stars are dominated by a strong fundamental radial mode, and then the other ridge is not. And another interesting related factor here is that when we look at the period luminosity relation for these stars, because they're classical pulsators, they want. We also see two ridges in the period luminosity diagram. So there's a fundamental mode ridge, but there's also a ridge that's at about twice that frequency. And so that's an interesting parallel that we really only noticed last week, that we have two ridges here and we have two ridges in the period luminosity diagram. So it could be that those are connected too. But it's an interesting question why for stars of the same temperature, you can have such a wide range in Remax. That's not explained.
They don't have modes.
Some of them do, yeah. So the rotating grid that Anuj is calculating, he's including degrees from L equals 0 to 3. The non-rotating grid that we trained the previous neural network on only has L equals 0 and 1 modes, and it has no rotation. And so with Anish's grid, not only do we get 100 times more models, but we have heaps more data on them, have different frequencies. So we can really do a lot more analysis. Another project that I'm working on, I didn't mention, is basically population synthesis of delta Scuti stars using his models. So if you draw random inclinations, random rotation rates from well-parameterized distributions, you draw binary companions, you put all these effects together, methodlicity distributions, mass distributions, what does your population look like? And that would be a really good application to try and make sense of this problem.
Other questions? Yeah, not one, but we think about questions. I guess still, since we're looking at this new max, of course, these modes, like the solar-like, they are intrinsically excited by a relatively well-known excitation mechanism. So have you used information about non-adiabatic pulsations in any of these something?
No. So unlike in the solar-like oscillators, where you basically have an envelope, right, and the strongest peaks are at the center of that envelope, and more or less every peak within that envelope is excited. You just don't get that for delta Scuti stars. It's not the case. Like our shell diagrams that I showed before, you often have gaps in the ridges in the shell where there's just a few radial orders that are not excited. We don't know why that's the case. We just have no means of predicting mode amplitudes. So no, we haven't used non-adiabatic models. We haven't tried to predict any amplitudes. We're just doing adiabatic frequency calculations at this point.
In some cases, I guess you can get at least or check whether the frequencies you observe are excited in the models. At least that's a condition that you can.
Yeah, it's not so much about checking whether they're excited. It's just whether, if you were to identify the spherical harmonics, whether the frequencies would match. But we basically assume that in our models, we can't tell whether a mode is excited or not. We can only tell what its frequency is.
I'm just thinking about other cases of B stars that people modeled years ago. Of course, if you observe a mode, a certain frequency, you can fit it perfectly with the models. But if your models your model does not predict an excitation. You know that something has to be wrong in the structure as well.
Right.
The video passes, you know, so it's
Yeah.
information.
So we do sometimes calculate the eta parameter, right? The driving minus damping for these modes. Energy's grid doesn't include that information. I know that some people do calculate that. I don't know how plausible it would be to calculate that for 20 million models. It'd be a fun project, but it would take a few years and an HPC or supercomputing cluster. But that would be a cool application even on a small scale.
Other questions? Online this.
I can check the chat. I think there may be something in the chat. Yeah, do you want to just?
No.
Nope.
Okay, well, if there are no more questions, well, thank you, Simon. Simon will be around tomorrow as well. So
Yeah, that's right. I'm here today and I'm here tomorrow. Sharing an office with Walter for those couple of days. So yeah, you can find it there. Thanks. All right, so if I stop share and then we stop, pause/stop recording.
Yeah.